Now we're going to talk about the pressure variation of a fluid as you go down into the fluid. So imagine like diving into a lake. The deeper and deeper you go into the lake, the higher the pressure is. And the first thing that we need to think about when we want to do this is we need to limit ourselves to what's called incompressible fluids. This basically allows us to simplify the math. And what an incompressible fluid is, it means that the fluid cannot be compressed. So water is effectively an incompressible fluid. Like all things in physics, this is not true 100%. It's not that there is a 0% ability to compress water, but it's very, very difficult to compress water, and it is effectively an incompressible fluid. For any situation that you will find on Earth, water is an incompressible fluid, right? So here you can test this just by filling a bottle with water completely to the brim. So notice that there's almost no air. There's a little bit of air trapped in my bottle, but there's almost no air. And if I try to squeeze this bottle, it's very difficult to squeeze the bottle. Say the same experiment with a bottle filled with just air, and I can clearly compress the bottle significantly. So air is not an incompressible fluid. It is clearly compressible, and I can change the density of the air, right? There is some amount of mass of air in this bottle, and by squeezing it, I am able to reduce its volume, which means that its density increases, right? Because I have density equals mass per volume. So when I squeeze the bottle, I reduce the volume and I increase the density. I also, by the way, increase the pressure. So there is more pressure when I squeeze the bottle than when the bottle is unsqueezed. So if we want to think about how the pressure changes as we move down in some fluid, we can think about the forces on a block of that fluid. So here what I have is just a box of water sitting in a lake. There's no physical box around the water. It is just that I am considering just this bit of the water inside of my imaginary box, right? So you can imagine just taking a still lake and then deciding to only pay attention to one box of the water in the middle of that lake. I am giving my box of water some mass M. I am giving the top of my box some area A, and I'm giving my box some depth, which I'll call H. Now, if we want to think about the pressures on this box, the best way to do it is to just use our Newton's third law or Newton's second law forces equation here. So let's think about all of the forces on this box. Well, first, let's just take care of X and Y. The X direction here. So I know that the box is not accelerating back and forth, right? It is just sitting there, which means that the total force in the X direction must be 0. The total force in the X direction must be 0 because I'm not accelerating in X. The only forces that are on my box in the X direction, so I'll just consider left and right here, is some force of pressure from the left, right? Just like on your body, the pressure force pushes inward on you, right? The air is pushing inward on you. The pressure force on this object pushes inward on it. We also have another force of pressure pushing the other way toward the right, so our box of fluid is getting squeezed. But because it's not accelerating in X, these two forces must, of course, be equal and opposite. So the pressure on the left side is the same as the pressure on the right side because my object is not moving. Okay, so the next thing that we can consider is the forces in the Y direction, which are more interesting. So I'm going to erase my X forces just to be a little cleaner here. I know that the box is also not moving in the y direction. So my net y force must also be 0, right? Because it's not moving down and it's not moving up, it must have 0 net y forces. So let's see if we can draw all of those forces. Well, first I know that there's gravity on the box, so there must be a force of gravity, and I'll choose up to be positive. A force of gravity equal to negative mg. We draw it as acting on the center of mass, but of course it is each individual water molecule being pulled down. So there is a force of gravity acting on this water as a whole, pulling it down. We also know that there's a pressure due to the atmosphere, which is also pushing down, right? So the atmospheric pressure must be pushing down on the water. So I can draw that force. I'll write it as F sub A. And the force of the atmosphere must be equal to the atmospheric pressure multiplied by the area, right? Because I know that pressure is equal to the force per area. So the force must be the pressure multiplied by the area. So this is my force due to atmospheric pressure. Note that as my area increases, the total force increases, right? So if I thought about the force on the entire lake, there's a lot more force pushing down on the whole lake than on, 1 meter square of it. Okay. And now I have 2 forces pushing down on my box. I have a force of gravity pushing down, and I have the pressure due to the atmosphere pushing down, giving me a force due to the atmosphere. Okay. 2 forces pushing down. If these were the only forces on my box, the box would clearly accelerate downward, right? Because there is a total force downward on the box. So there must be a counteracting upward force on the box, and that is the force of the water pressure from below. So I'll call this F sub P. It's going to point upward and support the water from below, right? So it's stopping the water from simply sinking, because I know the water is stationary. So I have my 3 forces, the force due to the pressure below, the force of gravity, and this atmospheric pressure force. I'm going to put a minus sign on this since that is a downward force as well. And now what I can do is I can write so I will box this off, my net y force equation as the negative PA, my force due to the atmospheric pressure, minus mg, the force due to gravity, plus the force due to the pressure at the bottom of the box. And I know that these things must add to 0. Okay. And I can rewrite this force of pressure as simply the pressure at this point, which I'll call P, and multiplied by the area of the box. And because I made my box symmetric here, I can just say that the area at the bottom of the box is the same as the area at the top of the box, which is just A. So I can write that P times A, my force due to the pressure, equals the atmospheric pressure times A plus mg. Okay, so assuming I know atmospheric pressure and I know the mass, and I've picked the area of my box, I could solve for the pressure at this depth. But I can actually be a little more clever about this if I realize that the mass of my box of water here actually just depends on the area that I chose, right? If I made a bigger box, my mass would increase. If I made a smaller box, my mass would decrease, right? So I can actually write down my mass of my water as the density of water multiplied by the volume of water that I chose, right? This is just my density equals mass over volume, which I've solved for mass. And I can rewrite my volume of the cube as the area of the top multiplied by the height. So I can really rewrite my mass as the density multiplied by the area multiplied by the height. And this nicely takes into account that if I pick a larger area or if I pick a larger depth, the mass of my water increases, right? The density of my water is constant, but if I choose a larger volume, I get more mass in that volume. Okay, so now I can write that the pressure multiplied by the area, my force due to the water pressure from below, looks like the atmospheric pressure times the area plus the density of the water multiplied by G multiplied by the volume, which I'm going to write as the area times the height. Now notice that there's an area in each of my terms, so I can take that out, and I get that my pressure looks like the atmospheric pressure plus the density of water multiplied by gravity multiplied by the height. And in this case, H stands for depth, not necessarily height. Okay, so the pressure at some depth here is equal to the atmospheric pressure plus the density of water multiplied by gravity multiplied by the depth at which I have gone. All right, let's just take a second to make sure that this equation makes sense. All right, one logical double check would be if height equals 0, that is I'm at the top of the water, then my pressure should just be atmospheric pressure. And indeed that's true, right? If I set H equal to 0, then the second term goes away and my pressure is atmospheric pressure. So at the top of the water, my pressure is atmospheric pressure as expected. As I go deeper and deeper, I get more and more pressure in a linear fashion because there's more and more weight of water above me pushing down, right? So for every bit that I descend, I get some amount of water above me pushing down, increasing the pressure, right? The density of water, so if water was more dense, then the pressure would increase faster because the weight of the water above me would be greater. Likewise, if I was on a different planet with a larger G or a smaller G, then my pressure would increase more or less, depending on how much gravity is pulling down. Again, it's about the weight of the water above you that is pushing down on you here. Okay, so this is our equation for pressure as a function of depth within some fluid.